Okay. Let's see here. One current slide. All right. So the t-test, this is what we're going to talk about for the rest of today. That is another test statistic that allows us to see the difference between groups and assess whether it is a significant difference or not. This is who came up with the t-test, William Seeley Gossett. It's a test statistic that that's used to compute. Let's try that again. It's the test statistic computed to test the null hypothesis about a population mean when the population standard deviation is unknown, and you're estimating it using the sample standard deviation. Now, let's take a break and think that through. How often do we know any of the population parameters, mean or standard deviation, if I have a research question? How often do we know that?
Mostly we'd have to figure that information out before we could test for that, right?
Right. And very often getting any sort of statistical information about a population is really hard. Why is it hard?
It's changing. It's not a static set of information.
That's true. What's another reason?
It's hard to get into contact with everyone.
Right.
Another one that's sometimes when you ask a question, sometimes people will answer it thinking or trying to make the person asking the question happy by answering what they think they want to hear.
Right. So yeah, that goes into bias and then faking good, faking bad, all very cool things we'll talk about again in research. But specifically with a population, that implies everybody in a specific group is counted, right? That's a lot of people. It is hard to do, which is why the bulk of statistics is done with samples, smaller group, and not just like 3 people that are representative of an entire population. That's bad stats. It needs to be a larger number, but smaller than the entire population. But because of that, we very rarely will know the mean and standard deviation of the population. So this test was created so that you can use the sample standard deviation, which you have, to then approximate the population and determine whether there's a significant difference. Okay. So a one sample t-test, we use this instead of the z-test when the standard deviation of the population is not known. So again, this is how we would calculate the t, right? We've got our sample mean, sample mean minus the population mean divided by the sample standard deviation divided by the square root of your sample. Now, this is a new idea here, the degrees of freedom. It is notated by DF, it's usually italicized, and that is your sample minus 1. We'll talk about degrees of freedom in just a minute. It allows us to account for some level of error in our approximation of the standard deviation. So a t-distribution is a family of curves, each determined by its degree of freedom, the number of scores that are free to vary in calculating the statistic. We use this when the population standard deviation is unknown and the standard error is estimated for the sample standard deviation. It's an important difference that we can find between the Z and the T statistics is because the standard deviation is estimated from the sample data. The denominator of the T statistic is subject to sampling error. Because again, we're not using the population standard deviation, we're using the sample standard deviation. Okay, so that is the different sets of curve. Oh yeah.
Sorry to interrupt, just backtrack.
No, it's fine.
Real quick. So in the one sample t-test, that's when we don't have the standard deviation. But we don't know it. But in
that's right.
the t-test, it has standard deviation in the formula?
So backing it up, we use a t-test as opposed to a z-test when you don't have the population standard deviation.
Okay, so
you then use it. You use
okay.
Right. So you need the population standard deviation for a z-score to determine the z-test. But if you don't have it, right? Let's say don't have that data, you can use a t-test. And what you do is you use your standard deviation for the sample.
Okay.
You insert that. That's what this is right here, that S,
Okay, perfect.
instead of being the mu or the sigmoid, right?
Yeah,
Anyway, yeah. This is not helpful, but
yeah,
anyway.
no, I know the symbol. Okay.
Okay. All right, yeah, and let's talk about that real quick. So the degrees of freedom, again, this is going to be for a normal curve. You're going to see this line, okay, right here. If you have 20 degrees of freedom, you can see it's this dotted line. So it's approximating the curve, the normal curve, but you see there's some small difference. If you have a degree of freedom of 5, it's, wait, I went back. So this one here, so this one was smaller. This guy over here, and then you've got the dotted line for degree of freedom of 1, okay? So those are the sampling distribution of the t-statistic. It shows that it isn't normal, so we can't use the standard normal distribution, right? It's approximating it, but it's not identical. Okay, so let's practice one of those one sample t-tests. So a random sample of 280 white females who worked full-time in 2014 were polled to figure out what their income was. We found that the mean earning was $41,653 with a standard deviation of 29,563. Okay, small standard deviation or large? But just from the get-go.
It's a pretty large standard deviation.
That is very large, right? Again, if we're looking at variance, if your mean is 41,000, that means you probably have people in the 150s and probably have people making close to 0, right? Large variation. Based on the data from the US Census Bureau, again, census, hint, 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 population, we know that in 2014, the mean earnings for women was 39,621. But we do not happen to know the standard deviation. So we don't know it. We want to determine whether the sample was representative of the population of all full-time women workers in 2014, right? So perhaps this is geographically interesting, right? If you got a sample that was located in Grand Rapids, let's say, and you wanted to know if it mirrored the national average. So you just want to know if it's different or is it the same? Another way to say it. So let's make a few assumptions. So our assumptions are as follows. A random sample is selected. We didn't stack the deck, right? We randomly asked a specific sample. Because our N is greater than 50, right? We asked 280 people. It's greater than 50, so we can assume that it's normally distributed as much as possible. And the level of measurement of the variable, which is income, is an interval ratio. Goodness gracious. So that's step 1. Step 2, we're going to state the research and the null hypothesis. My null hypothesis is that the income of the sample is the same as the national average, that it equals 39,261. The alternate, or the research hypothesis, is that this sample is higher, has a higher income than the national average. And my stated alpha is 0.05, okay? Again, your alpha is probably always going to be 0.05. Unless I give you something else, you can go on and assume it's 0.05. So we are going to have to use the t-distribution. So step 3, select the sampling distribution and specific tests. We have to use the t-distribution and the t-statistics because we are missing something. What are we missing?
Standard deviation of the population.
Exactly. So we're going to be using the standard deviation of the sample since we don't have the population, but because of that, we cannot use a z-test. We have to use a t-test. So first we have to calculate the degrees of freedom associated with our test. Again, degrees of freedom is n minus 1. N is 280 minus 1. That gives us 279. Now we need to compute the statistic, right? So the t-statistic is our sample mean minus the population mean divided by the sample standard deviation divided by the square root of your sample size. So here it is, 41,653 minus 39,621 divided by 29,563. divided by the square root of 280, which gives us a t-statistic of 1.15. Okay, I want us to take a quick break here and realize that's a lot of numbers on there, but really we haven't changed a whole lot about our formulas. This is all still pretty simplistic, right? Make sure you calculate the top, make sure you do the square root of your sample, and that you're taking into account the standard deviation of the sample. If you have the standard deviation of the population, you wouldn't be using the t-statistic, so that's a very good differentiator from the get-go. Okay, so now we need to make a decision. So given our research, we conduct a one-tail test because we're hypothesizing that our sample is larger than the national average. So that's a one-sided tail test or one-tail test. To determine the probability of observing a t-value of 1.15 with 279 degrees of freedom, we need to refer to a t-table. Now, you guys have that in your textbook. Let me pull one up here just so we can all be looking at the same thing. Have you guys seen it at the back of your book?
Not.
Okay.
I haven't been looking.
I can't believe you haven't. That's just so interesting. Okay. Again, once we use this in Excel, it just gives it to you. So it's going to be a lot simpler here. I'm trying to find a quick one here that you guys can look at. I want one that's clear. This one's not real clear. Okay. Oh gosh. I feel like I'm wasting time now trying to find this, and I'm getting a bunch of sites that are throwing up some junk. Well, mostly because our degrees of freedom are so huge. In your textbook, you would have, okay. Let me see if I can just show you.
I Googled t-test score table, and like the images that popped up seemed to be right, but
they're right, but they won't go that far high, which is fine. Yeah, the main thing is that our sample of 280, that gives us a standard degrees of freedom of 279. It's just quite high. Let's just keep going. So if you were looking at a table, the one, again, in your textbook, or if you find some online, you're going to see that oftentimes the degrees of freedom will start right around like 10, maybe even 50. Some of them will go up by increments of 50. Others will just go up by ones. So you can always estimate. So in your textbook, the degrees of freedom, 279 is not on there, but 300 is. So you can go straight in there and see what the critical value is. That's what we're looking for. So maybe this would be helpful. Even if it's not the right number, let me still share with you what the table looks like so you have, so we're all looking at the same thing. Sorry, I got too caught up in my own, like wanting to make it right for you guys. And okay. Okay, that's, nope. Why is this so hard? Here it is. Come on, table. All right. Okay, does everybody see this?
Yes.
Okay. So let's talk about this t-table real quick. So all of them are going to be very similar. You're going to have one row that's going to say one-tailed. The other one is going to say two-tailed. So first you want to find the one-tailed alpha. Okay. What's our alpha?
Is it 1.15? No.
That's our t statistic. That's the response we got for t. Our alpha we set at the beginning.
Oh, it's 0.05.
0.05. So I go here I am at one tailed, and I go all the way across till I get to 0.05. Okay. Now remember what I said, right? Like about strictness. If I was doing a two-tailed test, I would be right here, 0.05. But right now I'm doing one tail. Then what I would need to do is look through this right here. This is DF for degrees of freedom. This is why I didn't want to show you guys this one, because 100 to 1,000, it's a wee bit of a jump here. But for the sake of argument, this is what we're looking at. So if I was going down here, one tail, 0.05, I would go down, down, down. And at 100, I'm in the wrong column. I think this is the one I want to be in. Yes. I would be at 1.660, right? I want to make sure that I'm in the right column. Yes, one tail, 0.05. That would be 1.660. So let's go back to our lecture and see, what does that look like? What does it mean when you get a specific critical value? That is the critical value. That would be 1.660. That is if it was 100. Obviously, it's going to be a little higher than that. The critical value is right here. Why isn't this going forward? Is going to be taking a look at see if the value that you got for your t-test is going to be greater than that t-value. If it is greater than that, then you can assume that it's at lower probability, that it's hit that 0.05. Okay? So that's how we would do that. Your text has several other examples. I would really recommend you guys review that chapter and go through a few more of those examples so you know what it means and what it looks like. Another way you could do a t-test is by comparing between two means, okay? So that's saying I maybe have two samples, right? Two groups, and I want to see if their means are different. Is there a difference between the height of men in Kalamazoo versus Muskegon? Or is there a difference between the test scores on an exam in statistics by Dr. Woltel versus a different professor, right? So participants are only in one of the two groups. They're not going to be in both. This is different than a paired sample or a repeated measure design. I just need you guys to keep that in your back pocket. We'll talk about that later. A paired, yeah, I don't even want to get into it. So an independent sample t-test is that you have multiple samples and you want to see if there's a difference between the two. The question you're really asking there in terms of the research is the value of the difference, right, between the two means, is it significantly different than zero? In other words, using the stats class example, if the mean on a test for class A is 74 and the mean in class B is 73, is that difference significantly different than zero? Zero being my null hypothesis. Okay. This would be another example. So this is years of education in two groups. This is white and black men and women, okay? So we're dividing it in samples based on racial identification, and we look at the mean and standard deviation, and then we decide whether that difference is significant or if it's close enough to being zero, like it's just approximating to zero. Okay, so those are my two means. Eyeballing it, do they seem very different?
Not really.
Not really. But that's why we do stats, right? That's why we actually analyze it to see if it actually is maybe more significant than we thought. So first set of assumption, it's the same as what we did before, right? We have to go through that every single time. We have to assume that the independent random samples were used, that they were randomly sampled. We have to also have an interval ratio level of measurement. Years of education fits that criteria. Because both sample sizes are greater than 50, we can assume a normal population is not required. And the population variances are assumed to be equal. This is another big one. When we do this in Excel, that's going to be one of the choices. So we're going to be doing independent t-test variance equal. Okay. Then you're going to state the research and null hypothesis. So your null hypothesis is that they are in fact equal. Years of education are about the same. The alternate hypothesis is that they are not the same. Okay. We in here are not saying one is greater or less than the other, right? We're just saying they're not the same. We're going to be using a t-distribution and an independent sample t-test. All right, this is what we're looking at. So to compute the test statistic in order to get the t is we're going to be taking the sample mean of one minus the sample mean of the other, and then we're going to take the standard deviation of the difference of the two. Okay, it gets a bit more complicated for this one, so let's see if we can keep on tracking. We are first picking out the mean, right? Okay, so let's go back here. We had some information here that seems important. Here's our n's. We have our standard deviation that's written right here and our mean. So if we go forward, here's our n minus 1 times the standard deviation squared plus our n for sample 2 minus 1 times the standard deviation squared divided, right, by the 2 sample size minus 2, okay? We're gonna just keep on tracking. Remember, you guys are never gonna have to know these by heart. You're gonna have access to all these. Yeah, what's your question?
So where does the 2 come from? Is that just like because there's 2, just being 2 sampled?
Because there's 2 samples.
Okay, cool.
Yep. The degrees of freedom are gonna be the combination of the 2 sample sizes minus 2. So your degrees of freedom here is 531. So then you take your 2 means, one was 13.88, the other one was 13, and you divide it by, here's your standard error that you've got right here, the 0.35, and you get 2.51, okay? So if I was going back to my 0.05 alpha, right, on that table of t-test, it's gonna be very similar actually. I'm gonna go down and let's do that together just so we don't lose track of what we're doing. Okay, here we are. We start at the top. This is now a 2-tailed test. I go across 0.05 and then I go down. What was my degrees of freedom? It was high. 500s, right? Okay, so even if I have a conservative at 100, right, 1.984, that is my critical value. Does my t-value exceed that? So my critical value is 1.94. Let's remember again, what was the t-score we got? 2.51 is my t-score. Which one is greater?
2.51.
2.51 is greater than 1.96 or whatever that was any time of the day, right? So what is our decision? Whoops, it's not clicking. Here we go. Because of that, I can then reject the null that they have equal years of education. So here's how I would write it up. A 2-tailed independent sample t-test revealed that Caucasians, and in there I would write the mean and standard deviation, had significantly more years of education than African Americans, again, insert mean and standard deviation, comma, and then you put your test t statistics. So you'll notice it's t, and in parentheses here, that's your degrees of freedom, your 531, equals 2.511. That was your t statistic that you got. And this is the p-value. Now, all honesty, you are not ever going to be calculating this on your own. This will just be given to you, spit it out via Excel. But as we can see, that was more significant. In fact, this is just for funsies. Okay, let's go back to 2-tail. We know now that it's 0.01, right? So let's go down and see what is the critical value. So at 1,000, it's 2.581. So we could see like right in between there was our critical value. So that's why we were at like that 0.01. This is 0.010. We were at 0.012. Okay. For the purpose of this class, your goal is to understand how do you calculate a t-statistic? How do you calculate or find a t-critical value? And how do you determine whether you reject or fail to reject the null hypothesis? You will be asked to do this by hand maybe once. The bulk of what I want you to know how to do is how to do it on Excel, which will be very much point click, far easier. Questions about that?
So are we going to be running through this again next week a little bit more, or are we, like, after this, is it just like on us to double back to, you know, refresh ourselves, or are we going to continue a little bit more?
We are going to do it in class next week in Excel, because that's going to be our lab.
Okay, perfect.
But reviewing this in the textbook, again, there are so many examples. Look back in your text and practice a few.
Oh, no.
Just so you know what it looks like and understand it. But yeah, otherwise we'll go through it in Excel, because again, that's the big takeaway.
Okay, no, perfect. Is there like, so in the book, does it kind of show us how to do it like on paper, like through hand?
Yes.
Okay.
Yeah, you're going to have that exact formula, and they're going to have you go to the back of the book. They're going to pick like nicer sample size and degrees of freedom, where you can go in the appendix, or oftentimes what they do is they truncate the table from the back of the book and they put it right there in the example, and they just show you the part that you need to look at anyway.
All right,
Make
perfect.
it easy.
Oh, thank you.
No problem. Okay. Now, this is when you do hypothesis testing with two sample proportions, okay? We are not looking at populations at this point. We're using proportion. So is there a difference in education as a function of whether you were born in America or in a foreign country? So the proportion of, so again, proportion, you want to hear ding, 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 that's going to be a percentage, right? That's what we're looking at. Proportion of first-generation Hispanic Americans who earned a bachelor's degree or higher was 0.11. The proportion of second-generation Hispanic Americans with the same response was 0.21. That's proportion 2. There was a total of 899 first-generation Hispanic American versus 351 second-generation Hispanic Americans. Okay, so we've got two, right? Proportion 1, proportion 2, sample size 1, sample size 2. We're going to use a z-test for this because the measurement of the variable is not interval ratio. We're using a proportion that is nominal. Okay, the way we would do that is we would state that our null hypothesis suggests that our proportions are going to be the same. There's going to be no difference. The alternate research hypothesis is that they're not the same. There is a difference, right? Then we would calculate z, which is the proportion 1 minus proportion 2, and we're going to do the standard error of proportion 1 minus proportion 2. The standard error, as you can see here, is the square root of proportion 1 times 1 minus proportion 1 over the sample size, plus proportion 2 times 1 minus proportion 2 over sample size 2. Okay. This is what the numbers look like when you plug them all in. You end up with a standard error of 0.02. You then add in the two proportions and you get a z-score of -5. We know z-scores. Is that a big one or a little one?
It's huge.
That's very big. So yes, there is a significant difference in educational levels between first and second generation born Hispanic Americans. Okay, so we would, what's the language we would use?
So we'd be failing to reject, correct? What was the original claim?
So, okay, this is a good question. This tells you the whole story.
Okay.
H1 is your alternate or your research hypothesis, which states the proportions are not going to be the same and there's a difference. The null hypothesis, which is always going to be H sub 0, is that they are the same. So how do we respond?
Okay, so does anyone else want to take this one? I don't want to always be, hogging the, talking. Anyone?
Fail
Go ahead.
to.
Okay, and which one? So you're saying fail to reject?
Yes.
So in this one, remember, we are always making a comment. Reject or fail to reject only applies to the null hypothesis. So if I say I fail to reject the null hypothesis, in other words, I'm saying the null hypothesis is correct, that the proportions are the same. Are they the same?
Yeah.
This z-test is telling me there is a huge difference.
Sorry, I was just focusing on how we would talk about the equations in the far left.
Oh yeah. Okay. So yeah, once you get this.
How we would read that. I didn't know that we were looking for an answer with that.
Oh, sure. Yeah, no, it's no problem. So again, with a z-score of -5, if we're remembering our z-table, quick reminder, right? The z-table, your mean is at what number? Your mean is 0, right? So, there's my doodling. If my mean is 0, each standard deviation here is a different score. That's z-score -1, -2, -3. I am way out here in the tail. So that's very significantly different. So I would reject the null hypothesis because they are in fact not the same. So I reject. Okay. We are going to be doing these not in SPSS. We're not going to worry about that. Okay, that's actually it. So this is the last piece on proportion. For the purpose of quizzes and exams, you need to know what is your alpha, how do you set your alpha, and what's the most common alpha level, right? We know that's 0.05. You need to know what is a degree of, go ahead.
Sorry, I can't really hear you right now. Is that just me? Oh, I hear it. It's kind of glitchy.
Oh, that's not good.
Okay, no, I think it was just a split second. I don't know.
Okay, it fixed itself. You can hear me now? Okay.
Yeah.
All right, so alpha, how do you set it? And what's the most common number? Go ahead.
Okay, so alpha is most common number, 0.05.
Yes.
And is how we determine how to set that because we feel comfortable with that number?
That's exactly right. That's the amount of risk we are comfortable with in making a statement about our research hypotheses. Yep.
All right.
Then you need to know what are the degrees of freedom, right? How do you calculate it? You need to know the difference between a left-tailed, right-tailed, and more generally, what's a one-tailed test versus a two-tailed test? What is a null hypothesis versus your research hypothesis? What's the p-value? And then when would you actually be using a t-test versus a z-test? And that's it.
Okay.
Questions about this lecture? It's a lot of new data. So next week, we're going to actually do it in Excel. I'll practice a couple examples with you guys so you know how to do it. And we'll go from there.
All right, perfect.
Sound good?
Sorry, just so that I can avoid my mistake from today, what's due next week?
Let's pull up our syllabus so everyone's on the same page. So next week is November 4th. There's nothing that's due. We're going to be practicing the lab and getting it ready so that you can submit the lab the following week.
Okay, thank you.
No problem. It's a good question. Any other questions? All right. then I hope you guys have a wonderful rest of your day, and we will see you next week.
Yeah.
Bye.
Bye.